let's start with hydrogen today. Let's quickly, and I mean quickly, dive into the calculations. Here's where we're going to start. We're going to derive the hydrogen electron energy levels. Hydrogen electron energy levels will tell us a lot about not only the energy, but it will also tell us the position of the electron, so we can actually look at what the orbital is. This right here is the Schroedinger equation. And it says that the H, which is the Hamiltonian, and the little hat means operator, if we take this and operate on the state function, and the state function gives us all of the possible orientations of things we can measure, like energy, but also like position. And all of this is in a multi-dimensional space, which we won't dwell on that now. And then over here we have an E, which doesn't have a hat on it, and that same state function over here. The E is the values that we return from this. And in this case, we're concerned about the energy values. So if I take the state function, operate on it with this thing, this Hamiltonian, then we get the energies. Hamiltonian is the expression of the energy. So here's the energy values that we're going to come up with. Now let's break out the Hamiltonian. The Hamiltonian is mass. We know what the mass is. H bar. H bar, it's got a little mark through the top of the H there, and that stands for Planck's constant over 2 pi. Now Planck's constant that's quantum. That's the whole thing about quantum mechanics, about quantum chemistry, is that things are based in little steps or quanta. Then this thing, upside down triangle, is the Laplacian, and what the Laplacian does is take here's that number 2 out there, it takes the second partial derivative, because we're taking it with respect to x, with respect to y, with respect to z, and that is how we operate on the state function. Then out here we have this thing. This represents the kinetic energy term, and this represents the potential energy. This is the Coulomb type law form, and this is 4 pi times e to the 0. Now this epsilon is actually the permittivity. This is the constant that associates the units so that it comes out correctly as a potential energy. This r is the distance from the center of our coordinate system. Rather than x, y, and z, we're using an r here, which will change the Laplacian from with respect to x, y, and z. It'll be with respect to spherical coordinates, those that are based on a center and a radius at different angles. Magnitude of the radius and 2 angles gives us any point in space. Then we have E, that's the electron charge. Now why are there 2 of them? Why is it E squared? Why E times E? Well, the charge on the proton is plus, the charge on the electron is minus, so it's E squared, and this gives us an attractive potential rather than a repelling potential. Here are the spherical coordinates: a radius, a theta, which is one of the angles, you could think of that as elevation, and phi, you could think of that as rotation. So hopefully your mind can handle all that. Okay, I'm at the marker board. Isn't that interesting? V as a function of r. And I think we've just went over this, so this should be fresh in your mind. Then we have the full Hamiltonian equation, or actually the full Schrodinger equation, spherical coordinates. Okay, let's do a visualization of this. What I'm going to do is put the z-axis, that's supposed to be a straight line, but this is the z-axis, And I'm going to make this cross the line, the x-axis. If you're only in 2 dimensions, the z-axis would really be the y-axis. But anyway, in 3 dimensions, I'm going to make the y-axis, I'm going to draw it at kind of an angle, but think of it as sticking out of the page. And the spherical coordinates are going to be composed of the r radius and these 2 angles. So we need to describe these 2 angles and get it straightened out in our head. The theta angle would be coming from the z-axis down here. So the theta at 0 would be up in this direction. So if cosine of theta is 0, then that's going to be 1, and all of the r length is going to be on the z-axis. Now, what if phi is, how come I don't have anything about phi? Because if it's cosine of 0, it's all going to be 1 here, and the phi angle doesn't have any effect on it. Now, the phi angle starts at x and goes this direction. So phi of 0 is right on the x-axis. Phi of pi over 2 is on the y-axis. So the x-axis is going to be r sine of theta. If it's all x, it's going to be all the way down here, and theta is going to be pi over 2. And the phi angle is going to be 0 because it's right up here. If it's all y, it's going to be r sine of phi, and phi is pi over 2, so it's all on the y. And the theta angle is going to be equal to pi over 2. Or does that make any difference? Let's see. If theta is pi over 2, that still makes it in the correct direction. Okay, that all makes sense. I just fixed this. This was cosine, it should be sine. Because if both of these are pi over 2, then both of these will be 1 over here. The theta will be pi over 2, and the phi will be pi over 2, and that'll be the y-axis when that's true.